Hi, this is Professor Sartor, and I want to continue our lesson on approximating area under the curve. If you remember in our last video, we wanted to find the area under the curve for f of x equals negative x squared plus 5 from x equals 0 to x equals 2 with 5 rectangles of equal length. I've drawn the picture that we had from our last video just to remind us what we did. We have our curve, f of x equals negative x squared plus 5. We drew 5 rectangles in 2 different ways. One way was inscribed, and the other way was circumscribed. As we worked through the example, we were able to develop a few formulas that we're going to keep in mind for this video. Because we were having 5 rectangles of equal width, we were able to develop this formula for each rectangle, the width of each rectangle. We called it delta x, and that's b minus a over n, where a and b are over here. A was 0, b was 2, and n is the number of rectangles. We were also able to develop a formula for the right and left endpoints, and that right endpoints are delta x times I from I equals 1 to n. That generates a sequence, and that sequence will give us the endpoints of the rectangle that you see down here below the axis. Then we have a formula for the left endpoints, and that formula is just the right endpoint shifted over. So we have delta x, I minus 1, delta x times I minus 1 from I equals 1 to n. That also generates a sequence, but it's going to give you the right endpoints instead of, the left endpoints instead of the right endpoints. And then we talked about how to actually approximate the area. What we were doing was adding up each one of the rectangles. And that's where we have our sigma notation, was adding up those rectangles. We had to develop a formula for each rectangles. Finding the area of a rectangle is width times height. The width of each rectangle was delta x because it's the same for each rectangle. And then the height of those rectangles were defined by the curve at either the right or left endpoints. So this is the groundwork that we laid in the last video, and I want to pick up from here, diving in and making it more generalized. I want to spend a few minutes on a little clarification. In the previous example, we were able to draw our rectangles and notice that the right endpoints gave us the inscribed area, and the left endpoints gave us the circumscribed area. That's not always the case. I want to show you that with a different function, this different function here, f of x equals x squared plus 5, take a look at this one interval that I've drawn here. So you can see this graph is a little bit different. Instead of the parabola facing down, it faces up. And if I were looking for the inscribed area on this one, remember the inscribed area is smaller on the inside. So I would use this left endpoint to mark out the height because it is the lower y value. So I don't want you to get stuck on always using right endpoints for inscribed, because it really depends on the curve. And you can see here the higher y value is on the right endpoint, and that would give you the circumscribed rectangle. I want to take it a little bit further on this other picture over here. I've got negative x minus 1 squared plus 5. This just shifts our first parabola to the right 1 unit. And if we look at this rectangle right here, you can see that in order to get the circumscribed rectangle, we would not use an endpoint. We would use this value in the middle. That is the highest y value, the maximum, and that would give you the circumscribed rectangle. So in this example, you can see that we can't even use an endpoint at all to get the circumscribed area. So this brings us to a few modifications to our formula from before. So if you remember, before when we were finding the inscribed area, we had our formula as f at an endpoint times delta x. And now I'm changing it to, instead of an endpoint, this mi. Now the mi is the location of the minimum on that particular interval. So for example, if I had a picture that was like this, the minimum is here, which is f of mi. But if we go down to our x-axis, the x value would be mi. So it's the location of the minimum on that interval, the x value that goes with the minimum on that interval. For the circumscribed area, instead of using an endpoint, we have a capital Mi, and that capital Mi is the location of the maximum on that interval. So if we had a graph like this with a maximum value on it, that's f of capital Mi. If we go down to our x-axis, that would be capital Mi. We're going to call these the lower sum for the inscribed area and the upper sum. So this is a more general formula in which we don't assume that the left endpoint or the right endpoint are going to create those inscribed rectangles or circumscribed rectangles. So it might be some other value on the interval that creates the inscribed or circumscribed rectangle. So I just wanted to remind us of our goal again. Our goal is to eventually get to the actual area under the curve. And now we've defined this lower sum, and the lower sum is going to be all those inscribed rectangles. And that lower sum is definitely going to be less than the actual area. And the upper sum, we're going to have all circumscribed rectangles. So this area is definitely going to be larger than the actual area. So this brings us to another example. This example, we're going to use the function f of x equals x squared. We want to approximate the area from x equals 0 to x equals 2. We want to find the lower and upper sums, and this time we're going to make it even more general than last time. So instead of using a specific number of rectangles like 5 in the last example, we're going to use n rectangles, an unknown number of rectangles. So let's start by drawing a picture. The curve f of x equals x squared is a parabola. You know it passes through the origin. 1 squared is 1, 2 squared is 4. So our curve will look like this. And we're looking for the area from x equals 0 to x equals 2. So our a is equal to 0 and our b is equal to 2. from 0 to 2, A to B. Draw my vertical line up there, and this is the area that we are trying to approximate. So I'm going to work on finding the lower sum. Gave you a formula for the lower sum a moment ago, and that's the sum of I equals 1 to n, f of lowercase mi times delta x. That lowercase I is the minimum on the interval. So I'm starting off with this formula, and the first thing that I want to work out is delta x. Now we are still going to be using n rectangles of equal width. Because we're going to build those rectangles with equal width, we're going to be able to use our formula for delta x that we developed previously. So our formula was b minus a over n. Our b is 2, a is 0, and we're going to leave n as unknown. So we've got our delta x as 2 over n. So the next thing that we want to think about is our mi. So remember what that means. That's our minimum on the interval, or the location of the minimum on the interval. So what I'm going to do is go over to my picture, and I'm going to draw a sample rectangle. A sample rectangle is where you just pick a spot somewhere in the middle, you draw your vertical lines for the rectangle, and you just take a look at what you see. Now, since I'm trying to find the lower sum at the moment, I'm interested in inscribed rectangles. So the inscribed, I need the minimum on that interval. And in my sample, there's my sample rectangle, the minimum is going to occur at the left endpoint. So that left endpoint is going to give me the lowest height and the inscribed rectangle. So my mi, that should be lowercase mi. For this example, I'm going to use the left endpoint to get that minimum value on the interval. So previously, I gave you a formula for the left endpoint, and that formula for the left endpoint was delta x times I minus 1. Now this formula for the left endpoint will work for this example, but I want to give you a more general formula for the left endpoint. The more general formula is going to be a plus delta x times I minus 1. So the reason why I'm modifying it to be a is because if our a is something other than 0, we need to account for that shift over to that starting point. So let's work out for this example what that mi would be. So our a is 0 right here. We just worked out what that delta x is. That's 2 over n. And I minus 1 will be left. Just like that, because that's that's the way that we generate the sequence for those left endpoints. So I'm going to start substituting this information into the formula for the lower sum. I have sum I equals 1 to n. F of, I've got my mi right here, 0 plus 2 over n times I minus 1 is 2 over n times I minus 1. That's what's going to go inside F. And delta x is 2 over n. Now I'm going to rewrite f of 2 over n times I minus 1. Everywhere I see an x in my formula, I'm going to change it to 2 over n times I minus 1. So since my f of x is equal to x squared, I'm going to write this as 2 over n times I minus 1, all of that squared, times my delta x, which is 2 over n. From here, I'm just going to start using some algebra to simplify. Got sum I equals 1 to n. I'm going to apply the squared. That's going to be 4 over n squared times I minus 1 squared times 2 over n. Sum I equals 1 to n. I can put together 4 over n squared and 2 over n to be 8 over n cubed. And I'm also going to multiply out this I minus 1 squared. That's going to become I squared minus 2I plus 1 when you FOIL that out. Now, one of the properties of the summation notation is that you can pull a constant outside the sum, and even though that n is a variable, it is not the variable in the sum. So we're able to pull that constant out because the variable in this sum is I. So we have 8 over n cubed times the sum of I equals 1 to n of I squared minus 2I plus 1. Then we're going to be able to apply our sum to each individual term to make it sum I equals 1 to n of I squared minus sum I equals 1 to n of 2I plus sum I equals 1 to n of 1. So, continuing on, I mentioned a moment ago that you can pull a constant out of the sum. So I'm copying down the first bit here, and when I get to this second summation, I have a constant of 2, which I can pull out of the sum. Everything else I'm writing the same. So the reason why we've broken it down to this point is because we have summation formulas that we're going to use to simplify each one of these. I left off the squared on this one. So we have some summation formulas that we're going to use to simplify this. And the summation formulas, I'll write it over here, sum I equals 1 to n of I squared is equal to n times n plus 1 times 2n plus 1 over 6. The sum of I equals 1 to n of I is n times n plus 1 over 2. And the sum of I equals 1 to n of a constant is that constant times n. So that's how I'm going to simplify each one of these. So for the first one, sum I equals 1 to n of I squared. That becomes n times n plus 1 times 2n plus 1 over 6. The next one, I've got a minus 2, and I'm going to use the formula on this portion, sum I equals 1 to n of I, and that's n times n plus 1 over 2. And then the last formula, sum I equals 1 to n of 1, we'll use the formula about summing a constant. So our constant is 1 times n. I'm going to keep going with some algebra to simplify, and what I'm noticing here is that having these fractions makes it a little bit messy. So I'm going to make them all have the same denominator and then pull that out, or factor that out. So to make them all have a denominator of 6, I'll multiply this one by 3 over 3 and this one by 6 over 6. So that would give me 8 over n cubed. And this one doesn't change. For this one, 2 times 3 is 6, so we have now 6 over 6. N times n plus 1. And then another 6 over 6 times n. So now because all of them have a denominator of 6, I can pull that 6 out, and then I won't have fractions inside here anymore. So now I'm going to do some multiplying so I can combine like terms. I'll start by multiplying n plus 1 times 2n plus 1. That gives me 2n squared plus n plus 2n plus 1. I'll then multiply right here. That will give me minus 6n squared minus 6n plus 6n. Can combine like terms in the parentheses. That's 2n squared plus 3n plus 1 minus 6n squared, and then these terms over here, minus 6n plus n, 6n cancel each other out. And I'll distribute this n. That gives me 3n cubed plus 3n squared plus n minus 6n squared. I can combine like terms again. Got 3n cubed minus 3n squared plus n. Now I'll get rid of the parentheses altogether and distribute this 8 over 6n squared. And I can go ahead and reduce that to 4 over 3n squared before I multiply. And then I'll distribute and get 12n cubed over 3n squared minus 12n squared over 3n squared plus 4n over 3n squared. And I can reduce this. I've just noticed that along the way I changed a 3 to a 2, which I do quite often. So I'm going to fix this. I've got this should be a 3, a 3, 3, 3, 3, and all of these should be 3s. I apologize about that. So now we'll reduce these to get, I apologize, I noticed it again. I changed my 2's to 3's and 3's to 2's. So right here, I changed this 2 to a 3, so this should be a 2, a 2, 2, which makes this an 8, not a 12. Okay, so now I think we're back on track. So the n cubes will cancel out. I have 8/3. Here we reduce to be 4 over n and this one reduces to be 4 over 3n squared. So that was a lot of algebra that we did, but just keep in mind that this is now the lower sum. I'm going to keep the upper sum as an activity for you. I'm going to tell you what it comes out to be. It comes out to be 8/3 plus 4 over n plus 4 over 3n squared. So with both of these formulas, remember that n stands for the number of rectangles. So if I were to choose a specific number of rectangles like we had in the last video of 5, then we could substitute 5 in for n, and then we would have the area with the lower sum, the inscribed area, the upper sum, the circumscribed area. Also in the last video, I mentioned that the way that we get a better approximation is to increase the number of rectangles. If we increase the number of rectangles, we're going to get less error on both the lower and the upper sum. We're going to continue to get closer and closer to the actual area. So essentially what we're saying, if we want to increase the number of rectangles, we want to allow n to approach infinity, and that's where we can introduce the limit into our formulas. So if we were to take our lower sum formula, which remember our lower sum formula is S of n equal to the sum I equal 1 to n, f of the minimum delta x. If we now allow our limit as n approaches infinity on this, we're allowing the number of rectangles to increase, and what that gives us is the actual area. So instead of it being an approximation, we get the exact area. We can do the same thing with our upper sum. It's a capital S of n. The limit as n goes to infinity, that's allowing our number of rectangles to increase. I equals 1 to n. F of capital M, that's the maximum on the interval. This will also give us the actual area. So let's do that for our example. We had, for our lower sum, we had 8/3 minus 4 over n plus 4 over 3n squared. If we take the limit as n goes to infinity of this quantity, we get 8/3. On this section here, because n is going to infinity, this whole fraction is going to go to 0. That's because n is in the denominator. The same thing happens with this fraction here. Because n goes to infinity, that fraction goes to 0. So we get 8/3 plus 0 plus 0. We get 8/3 by doing the lower sum. Our upper sum was 8/3 plus 4 over n plus 4 over 3n squared. If we allow the number of rectangles to increase to infinity, we find the same thing, that since n is going to infinity, this fraction goes to 0, and so does this fraction. So we end up getting 8/3 whether we use the upper or the lower sum. And 8/3 is the actual area under the curve. So now we're not only able to approximate the area under the curve with rectangles, we're able to find the actual area under the curve with this formula here. Limit as n goes to infinity, sum I equals 1 to n, f of ci times delta x. So notice that I'm not using the lowercase mi or the capital Mi. The Ci is any point in the interval. So our example before has showed that when we use the lower sum and we took the limit, we got the actual area. We used the upper sum, we took the limit, and we got the actual area. So it doesn't matter whether we use the lower sum or the upper sum or any point in the interval. We're able to find the actual area as soon as we introduce the limit. Once we allow the number of rectangles to go to infinity, it doesn't matter whether we use that lower, upper sum or any point in the interval.